think for so long, we've assumed that abundance stands in contrast to environmental protection, but that's not the case. It is not an inherent tie between environmental destruction and the production of energy. You can point to some use cases where it might look like that, but there are ways to decouple the two. And one of the key linchpins to that decoupling is nuclear power. And if one of the things that we care about is the preservation of nature, or maybe even more than the preservation, but actually the enhancement of ecosystems, all of this comes from the ability to manipulate our environment, which comes from massive amounts of energy. Energy is abundance, abundance is prosperity, prosperity is human flourishing. Hi, my name is Bret Kugelmass. I'm the founder and CEO of Last Energy, and we are trying to reinvent what energy means for planet Earth.
Chapter 1, The Nuclear Renaissance.
The ability for humans to be prosperous, the ability for humans to do things that don't require hard labor, the ability for people to do things that improve the environment around them, not just the environment as in nature, but the environment that they live in, their built environment as well. All of this is prosperity. All of this is human flourishing. And if one of the things that we care about is the preservation of nature, or maybe even more than the preservation, but actually the enhancement of ecosystems, all of this comes from the ability to manipulate our environment, which comes from massive amounts of energy. Energy is abundance, abundance is prosperity, prosperity is human flourishing. One of the challenges in progressing society is choosing which technological paths to go down. And we only have so many resources to invest to get from where we are today to where we want to go. And we want to set ourselves up for success. So when I think about planning for the future, out of all of the energy technologies to invest in, and it doesn't just have to be renewables or nuclear, we could invest in fossil fuels and just create more energy while also putting more carbon in the air and maybe decide that that's a fair trade-off too. But when I look across all of the factors that I consider, when you want abundance, when you want to be able to scale your technology, when you don't want to run into resource limitations, when you don't want the negative externalities, when you don't want the impact on the grid that renewables might have, nuclear wins across almost every category except for a historical societal distaste for it. But that's changing now too. And so I want to start with what has the best physics advantage over any other energy source, and then solve the policy and solve the social problems to be able to give it its best shot at delivering the future that we all want. If we want to be able to mitigate climate change, if we want to be able to improve human prosperity, improve the standard of living to the highest standard for everybody across the world, most people don't realize just how much energy that's going to take. It simply comes down to how much you get for how much you put in. And renewables take a tremendous amount of energy and materials to be able to deliver that energy. So it might feel like the fuel for solar is free because it comes from the sun, but that's not the fuel for solar. The fuel for solar is the materials that went into the initial solar panels themselves that only last 20 years. And so those materials themselves have to be dug out of the earth. Those materials themselves come with a carbon footprint that simply can't be ignored. And when comparing solar to nuclear, the amount of material that is required, the amount of engineered material that is formed into steel or concrete or the complicated electronics inside, that material requires 1,000 times more material for solar for the same amount of energy produced. So yes, it feels good to be in the sun. It feels good to think, oh, we have this infinite energy source if we could only just grab it. But again, that belies the reality of what went into making the solar panel itself from the get-go. For nuclear, it's 1,000 times less to get the same amount out. And so for me, it's as simple as that. It's just a logical first principles argument of how much you put in to how much you get out. Everything else that drives up cost is policy and bureaucracy and other implementations in the real world that might not have anything to do with the core technology itself. But if you want to start from the most advantageous position as possible, It starts with energy density. Energy is the root of all materials. Energy is the root of transportation. Energy is the root of everything that you touch and everything that you do and everywhere that you move around the world. It all comes down to energy, and we are going to need so much more of it. What's so amazing about nuclear power is how much you get from how little you put into it. You have a 6 order of magnitude advantage over chemical energy. And the amount of material that goes into a nuclear plant when compared to renewables on a per energy basis, you have a 3 order of magnitude, 1,000 times advantage using nuclear power. And so if we're going to increase the scale and the abundance of energy around the world, from a first principles perspective, it has to be nuclear.
Chapter 2. Understanding nuclear manufacturing.
Nuclear energy, unlike most other energy sources, exploits atomic physics. By splitting the atom, you are able to release so much more power than by splitting a chemical bond in a material. And the material, the amount of mass that you need to produce a certain amount of energy, that is the core factor that decides how efficient a system can ultimately become. A nuclear plant has several different key components or key pieces of equipment in it. One of those is a nuclear reactor. Another is a steam turbine, what has spinning blades moving different pressures of steam across in order to spin a magnet and create electricity. The nuclear reactor part, though, it really isn't that mysterious. It's pretty solid state. You have a series of ceramic uranium pellets stacked within rods that look almost like a heat exchanger of sorts. And then by passing water over it, that water is able to activate the nuclear process and also be able to carry the heat away to eventually boil more water into steam, which then spins that turbine that we spoke about. And so with those 2 key components and then a whole bunch of pumps and pipes, you've got a nuclear power plant. What's pretty impressive about the nuclear industry is that it actually does provide 10% of all world electricity and 4% of global energy. That's not nothing. The problem is a lot of that infrastructure was built many, many years ago. And then over time, we've lost our way with both the know-how and also the policies and the regulatory constructs that allow for efficient production. And so, yes, when people critique nuclear and say it's too expensive, I say you're absolutely right, and that's the problem to solve. There aren't inherent challenges to manufacturing any of these components at scale. It's really the systems integration effort and your product design criteria that must really be ironed out in order for it all to come together and work out. While there are all of these other costs that have crept into the nuclear systems to drive the cost up, on a first principles basis, it should be orders of magnitude cheaper than any other energy source that we have. So solving that problem was key for Last Energy. Last Energy's product is a 20 megawatt plug and play factory built micro nuclear reactor. Our concept is to, rather than reinvent the nuclear core technology, just apply high throughput manufacturing principles to the existing technology. My background before starting Last Energy was running the Energy Impact Center, which was trying to diagnose what were the true challenges holding back energy technologies, and we decided to focus on nuclear specifically. After interviewing over 865 subject matter experts in 1 year alone, what we concluded, or the thesis that we developed, was that the problem holding back nuclear energy wasn't really new technology. It was applying the technology that had already been developed in a more cost-effective manner. And that means manufacturing at scale. So the first step is to design your power plant system using all off-the-shelf components to really make it a supply chain and a procurement and a systems integration effort rather than material science or a reinvention of physics effort. After we've designed our system to fit within certain volumetric and weight constraints, all of a sudden we enabled it to become entirely factory manufactured. And that factory manufacturing is the key to be able to apply automated manufacturing processes, high throughput manufacturing, to be able to work with materials in a way that you can only do indoors rather than out in the field. That makes it inherently replicable and then over time, lower and lower cost. The traditional workhorse of the nuclear industry, the pressurized water reactor, looks and feels and acts almost exactly like a coal plant. It has pumps, it has pipes, it has water moving through, it has steam being created, it has the same types of control systems. The only thing that's different is the boiler, your initial source of energy, your hot rock. And even that is a pressure vessel that's very similar to hundreds of different industries and tens of thousands, if not millions, of installations that have existed around the world for the last 150 years. That's the magic of the standard pressurized water reactor of fission technology, is that it feels and acts so much like so many other industrial technologies and can use that same existing supply chain. That's why the pumps, the control systems, the pipes, the materials are actually relatively affordable compared to your overall systems cost. When you move towards a new technology that deviates from the standard supply chain, one that uses exotic materials, all of a sudden you have to spread out that R&D cost and you have to learn your lessons over a longer period of time on fewer facilities. This ultimately drives up the cost, not just a little, but perhaps orders of magnitude more than a technology that already starts off using proven technology. The traditional way of building nuclear power plants is what's called stick-built construction, where just like any large construction project, you'll have hundreds, if not thousands of workers out on a site at a specific time, moving around concrete trucks and cranes and loading steel and having welders in sight. But all of that leads to potential quality issues, scheduling issues, and over time, those costs build up. Time is also another key factor to driving down cost, because all of these infrastructure projects require you to borrow capital. And the longer the period of time that you borrow that capital over, the more expensive the output of your energy will become. So by bringing everything back into a factory setting, you're able to increase the quality and reduce the time of deployment, thus making the entire delivered product cheaper as you build more and more. For many decades, the market incentives that were set up by how power was regulated led to utilities building bigger and bigger infrastructure. You see, it was a cost-plus model for many decades in our country. So the more that you built, the more money the utility can make. The incentives with big infrastructure, when all of the various stakeholders that are involved can get more money, they will get more money. And so in the cost-plus structure, or when the government provides a backstop or an insurance policy that tells all of the contractors, hey, it's okay if you run over budget or you run over time, that makes that an inevitability. And so what you want to do is you want to keep the pressure of the free market to allow for competition and force the various vendors and contractors involved towards higher levels of performance in delivering their product. If you remove that incentive, the worst is always going to happen. Time and costs will spiral out of control. It wasn't only until a couple decades ago did the market construct actually shift and make this a viable opportunity to have a cost-effective product. But then, of course, you have so many entrenched interests and the incumbents that have set regulatory pathways that help to lock in the old way of doing things. In many parts of the world, they are building new nuclear power. We have 60 plants under construction. There are just not so many in the Western world. You see, in the US, we stopped building energy infrastructure, and many industries in the energy sector fell out of favor simply because we started focusing on efficiency more. Well, that deteriorated our ability to deliver when we do have increasing energy demands, such as that now that we're seeing through electrification of vehicles or artificial intelligence. And so it's been a hard restart of the nuclear industry in the Western world. Other parts of the world are building it and they're getting better at it, and we want to see that here too. No matter what, even if we aren't seeing plants being built next year or hundreds of millions of dollars being invested or spent immediately on these projects, the tailwinds are incredible for the entire industry. You're building a broader base of support and you're building a sense of inevitability that this technology is important, and you're also marrying it with a very exciting futuristic technology as well. So I think that's what we're seeing a lot right now. We're seeing a lot of announcements, we're seeing a growing enthusiasm, and That's step one. And then you're going to see more and more interest come into the sector, more and more entrepreneurs come into the sector, more and more ways of doing things, more and more governments that also want to contribute. So what we're really hoping is that all of these announcements over the past few weeks and past few months, the marriage between big tech, AI, and nuclear is going to kickstart. It's going to achieve that activation energy in order to really be able to send the industry back into the innovation, development, and production mode that we've been hoping for decades. I would say the greatest pushback for advancement in nuclear technology comes from the incumbents in the nuclear industry itself. Over decades of rent-seeking behaviors and regulatory capture to create these defensive moats, they've created a legal construct that it's difficult for even them to supply a product into market. And so in many ways, the nuclear industry has become its own worst enemy and needs to get out of the way in order to allow the next generation of technologies to emerge and create a much more powerful nuclear industry, not just for all of the players, including the incumbents, that can be a productive part of the supply chain, but for Earth overall. It seems that over the last couple decades, there have been two wildly different paths for next-gen nuclear. One of those paths is to reimagine how you configure the proven existing technology, those pellets of uranium that are arranged in the way that we spoke about previously to have water pass over them. There's still many different configurations, and so that's one set of innovation in the nuclear arena. Another set is to use fundamentally different fuel types, use fundamentally different material science, use fundamentally different coolants, some that have been tried in the past and some that have never been tried at all. And that's a very different process for technology development within the next-gen nuclear arena. There are high-temperature graphite reactors, there are molten salt reactors, there are reactors that mix the fuel in with the coolant. There are many different cool ideas, and a lot of these the US government tried back in the 50s and 60s. Our thesis, looking back at that historical evidence, is that while all of these reactors work from a nuclear reaction perspective, it actually increases the maintenance and decreases the reliability of the power plant as it's operating over time. And so that's why we thought it was so essential to stick to the proven technology, stick to the existing supply chain in order to optimize system costs and not just reactor performance. Fusion is an interesting one because many people have this appreciation for fusion, or they think it's the future of energy. They think it's the ultimate energy source. And in my experience, I haven't found that to be true. It's actually hard to find a single characteristic of fusion that's preferable over fission. Most people don't realize that fusion is actually the higher radioactivity version of nuclear physics. And while I actually don't think that the radioactivity concern poses the health hazard that it's become in people's minds, I think you're going to lose that public support and lose all of the enthusiasm that's been directed to this unproven technology once people uncover that it is the higher radioactivity version. The difference between fusion and fission is pretty simple. It's almost in the words. In fusion, you're fusing two small atoms together, and in fission, you're breaking one big atom apart. Both release energy in different ways. When you break apart a uranium atom, the most common large atom to break apart, uranium-235, you're releasing about 200 mega electron volts, and a couple neutrons come off too, and it's those neutrons that continue the chain reaction. In fusion, because you don't have a chain reaction, you have to apply an incredible amount of energy to force two very light elements like hydrogen together in order to also release a neutron that gets expelled out into the world, but only 15 mega electron volts of energy. So when you put together your energy balance equations on a per unit energy basis, you're actually releasing 7 times as many neutrons in a fusion process than in a fission process. And those neutrons are what go on to make the environment around them radioactive. So I think no matter what technology you end up developing, the design for manufacturability is going to be the ultimate driver of cost effectiveness. And so you have to understand, what is it that we value in a technology? And if for energy, to achieve our goals of abundance and human prosperity, you have to be able to bring the cost down over time. The huge advantage that proven fission technology has is that the supply chain is already developed, and the development of that supply chain has already been amortized over so many other industries for the last 150 years. It uses steel and water and pretty basic materials. The minute that you have to switch up your supply chain to use more exotic materials, every single one of those components requires $1 billion R&D effort. And it's very difficult to make those systems cost effective, even if you were to build hundreds. You'd have to build millions of those systems to get the same economies of scale of the supply chain as you would for something else that's already been proven and exists in the real world today. One of the big advantages of switching to a model where to deliver energy, you do a lot of a small thing instead of one of a big thing is that you're able to build resilience into your network as well. You're actually also able to provide a different type of grid service. The alternative to wires is a way to think about it. So if you were to deploy the generation close to the demand, what you're able to do is unlock the ability to relieve the pressure on the grid that would have normally transported between the difference in space between your demand and your generation. And so among the many other advantages of building many and economies of scale of number of having these smaller systems, you're also able to deploy them in a distributed manner that has these inherent advantages as well. A traditional nuclear reactor, a gigawatt class reactor, would provide power for about 1 million homes or a big city. The technology that we've decided to start with for mass manufacturing, from the logistical constraints that we put into the design itself, brought us all the way down to 20 megawatts of power. It fits in about the size of a school bus. It can be road transported, dropped in a hole in the ground, and provide power for about 20,000 homes. But you can also build a whole field of these. And so some of our hyperscale data center customers want 200 megawatts at a time. We'll actually drop 10 identical 20 megawatt facilities rather than building a 200 megawatt facility. About a quarter of the Earth's power goes to industrial factories. Anything from pulp and paper to sugar processing to steel to aluminum. And all of these different processes require a lot of electricity, and some of them require heat as well. The type of technology that we're bringing forth can supply both heat and power, and that heat can be supplied up to 300 degrees Celsius. Now, not every factory can work with 300 degrees. Some require 500 degrees. So it's not the perfect fit for all industrial processes, but it does cover probably about half of them that exist today.
Chapter 3. The environmental concerns about nuclear.
Every time that there's a nuclear accident in the world, it is the behavior and pattern of the existing nuclear industry to exacerbate rather than downplay the reaction to that accident. What they use strategically is the fear from that accident to ratchet up the regulations in order to mandate more engineering services that they provide into existing facilities in a self-cannibalizing and rent-seeking behavior, rather than focusing their attention on being able to deliver a new product. After Fukushima, the industry lobbied for about $300 million worth of engineering analysis per existing plant that's already up and running in order to be able to capture more of the revenue from those existing assets. And so in many ways, this hurts all parties that want to develop new technologies and bring them forth because they might be subject to those regulations as well. And so the only way that we've found to overcome this is to work with the regulators and provide many clever arguments and find the regulators that are most amenable to performance-based standards rather than prescriptive standards that would force us to incur a $300 million penalty and obviously make our product infeasible. I think for so long, we've assumed that abundance stands in contrast to environmental protection, but that's not the case. The case is as societies become more prosperous, they're able to devote more time and attention to the environment and to beautifying and creating a world that we can all enjoy and cohabitate in, and that's healthy and clean for everyone. That comes from prosperity. And the best way to unlock prosperity is to unlock clean, affordable energy, to unlock energy at a scale orders of magnitude more than what we're producing today. It is not an inherent tie between environmental destruction and the production of energy. You can point to some use cases where it might look like that, but there are ways to decouple the two. And one of the key linchpins to that decoupling is nuclear power. Most of the environmentalists that are anti-nuclear are actually anti-humanists. They're Malthusians. They don't want to see progress. They don't want to see new technologies. They don't want to see development. And nuclear is really just a proxy for their other beliefs. Environmentalism has emerged into almost a religious fervor of sorts, where it's not actually about saving the environment, but about some other agenda in an environmental wrapper. I don't think anyone's arguing from bad faith. I think they're misinformed. Everyone just says the same things as the 5 closest people around them. There are very few independent thinkers on this planet. And so if all of the people in your environmental movement just assume nuclear is bad, and that's one of your rallying cries, it takes almost superhuman ability to reject that notion. Now, some people have done it. Some of the heroes that have emerged from the environmental movement to become extremely pro-nuclear and educate others, like Michael Schellenberger. These people have these superhuman powers to break free of what their community tells them, but that's too much a burden to ask for most people. Many people have a feeling inside of them that radiation itself is a hazard disproportionate to other types of toxic chemicals or other hazards in the world. And that feeling is okay. We have to acknowledge that feeling, but unfortunately, it belies reality. Radiation is just like anything else, and a nuclear reactor, just like any potentially hazardous facility, can be configured in a way such that when something goes wrong, it doesn't create a hazard. And so that should be the focus, rather than throwing the baby out with the bathwater and assuming that all nuclear is bad just because there is one component to it that is potentially hazardous.